in the Department of Electronics and Communication Engineering. Today, I'm going to discuss about the probability theory and stochastic processes. And in this, we are going to discuss about the operations on multiple random variables. So here are the contents which we are going to learn now. So in this chapter, we are going to learn what is expected value of the random variable and what is the expected value of random variable to function. So when it is a function, and what are the joint moments, about the origin, and what is mean and mean square value, and what is variance, and what are the properties of variance, and finally we will end this lecture with characteristic function. Okay, first coming to the expected value of a random variable. So what is expectation generally? We know that expectation is related to something will happen in the future. Here the same will be applicable for random variables also. So expected value is also known as expectation, average or mean value of a random variable. So here it is nothing but the average value of a random variable. For example, if you consider the random variable with set of events such as x1, x2 and so on and so on. So now if you want to find the mean value or expected value of a random variable, then you have to multiply the events with their probabilities and then we have to sum up together. So here if you see, it also indicates a probability weighted average of all possible values. So x1, x2 and so on, how many values we can take from a random variable x. Okay, so when you multiply the events with their probabilities, for example, event x1 is probabilities p of x1, event x2 is probabilities p of x2 and so on. So if you multiply them together and sum up together, it is nothing but the expected value or mean value. So here if you see, this is the formula for finding expectation or mean. So E of x or simply Ex is equal to integral minus infinity to infinity x fx of x dx. So where this integration tells us the sum. Okay. So here x is the event and fx of x is the probability density function. Okay. So which we have multiplied and summed up using integration. Did you understand? So here x and fx of x both are continuous events. That's the reason we have taken integration. Okay. So next coming to the discrete values. So consider random variable x as a discrete random variable. So with multiple events such as p of x1, sorry, x1, x2, x3 and so on n. So their relative probabilities are p of x1, p of x2, p of x3 and so on, p of x3. So now if you multiply the events x1, x2 with their probabilities p of x1, p of x2 and sum up together using sigma. Okay, sigma we have used. This indicates the summation effect. So mu x, which is nothing but the expected value or mean of a discrete random variable. Okay, so it is given by sigma I equal to 1 to n because we have taken n events. So xi px of xi. Did you understand? Xi is a set of events. So px of xi are their respective probabilities. So here we have seen a simple example. Okay, suppose if x is a random variable which is defined by the probability density function, fx of x equal to 1 by b minus a. So a less than or equal to x less than or equal to b and 0 otherwise. That means, so this probability density function is concentrated only in the limits or only in the values of a and b. And other than a and b values, it will be 0. Okay, now we need to find what is the mean expected value of this random variable. So which is nothing but given by the expression mu x equal to integral minus infinity to infinity x into fx of x So here x is nothing but the event. Okay. So take x as it is, and we know only probability density function, which is nothing but 1 by b minus a. Okay, differentiation of x. So here 1 by b minus a is nothing but constant. Okay, take it outside of the integration. So integral. So here limits are a to b because the probability density function is distributed only along a and b value. So integral a to b makes dx. What is the integration of x? Okay, this is nothing but x square by 2. So 1 by b minus a, x square by 2 along a and b. So 1 by b minus a, substitute the limits here. So b square minus a square by 2. So 1 by b minus a. So b square minus a square. So if you write the expression for it, b minus a into b plus a by 2. So 1 by b minus a into b minus a. So these two will get cancelled. So finally what will be left over? B plus a by 2. Did you understand the problem? Next, let us see another example. So here is one more example which is applicable for the discrete random variables. So consider the random variable x with the property mass function as tabulated figure. So here value of random variable x 0, 1, 2, 3. So these are set of events. Okay, and these are their respective properties 1 by 8. When event 0 happens, its property is 1 by 8. For event 1, it is 1 by 8 again, and for event 2, it is 1 by 4, and for event 3, it is half. Okay, then according to formula, so mu x equal to sigma 1 equal to n to n xi dx of xi. So xi is nothing but p of 0 into its property p1 plus p of 1 into p of x2 x1. Sorry. Next, 2, it is event 2. So, and p of 2 and event 3 into p of 3. So, 0 into 1 by 8 plus 1 into 1 by 8 plus 2 into 1 by 4 plus 3 into 1 by 2. So, if you take the LCM 8, okay. So, 0 into 1 by 8 is 0. So, 1 by 8 plus 1 by 2 plus 3 by 2. So, when you take LCM, you will get 8. Okay. So 1h1 plus, okay, 2 4s. Okay, 4 plus 2 4s. Okay, 17 total. Okay, in the numerator you will get total sum 17 by 8. Next, coming to the expected value of a function of a random variable. So here we are transforming. Okay, here we are applying transformation of a random on a random variable. Suppose we have a random variable x, okay, with its density function f(x) of x. Now, if we apply the function to produce the random variable y equal to g of x, here g is the function which we have applied on x, such that the output should be y and input equal to x. So just think it as a black box with input as x and output as y with function g. So how to find the expected value of a function of a random variable? See here. Suppose y equal to g of x is a real value function of a random variable x, then expectation of y equal to expectation of g of x, that is equal to integral minus infinity to infinity g of x f(x) of x dx. Simply we have to multiply that function with its probability density function and take the sum. Did you understand? And here are some of the properties, okay, which are applicable for functions, functions of a random variables. So for example, if c is a constant, so for a constant, if you apply integration, so e of c is nothing but that particular constant itself. Okay, so e of c equal to integral minus infinity to infinity c f(x) of x dx equal to, since c is constant, take it outside of integration, minus infinity to infinity f(x) dx. So here if you evaluate this integration, you will find one constant value only. So next, another property. So if there are two functions of random variables, so g1 of x and g2 of x, and there are c sorry, there are two constants available, C1 and C2. So then if you find expectations of these values, like expectation of C1 into G1 of x plus C2 G2 of x, that will be equal to C1 expectation of G1 of x plus C2 into expectation of G2 of x. So here what we are saying, so when you calculate expectation value of these both together by combining these two values together, if you find the expectation, this will be equal to constant times of expected value of G1 of x plus constant C2 times of expected value of G2 of x. So next coming to the mean square value. So mean square value is nothing but the second moment of a random variable. So here E of x is nothing but the first moment. Okay. So which is nothing but the mean. So mean square in the sense if you take the square value of a if you take the expectation of a square value of a random variable, it is nothing but the mean square value. So it also defined as the arithmetic mean of the squares of the set of random variables. Understood? So if you find the formula, so it will be given like this. So expectation of x square equal to minus integral minus infinity to infinity x square fx of x dx. Simply you have to take the square of the random variable and multiply it by its probability density function and find its sum. So that is nothing but the mean square value. So why do we need to find the mean and mean square value? Because mean tells us how the random variable is distributed over certain interval. So mean is exactly the average, the central moment. Okay. So after finding this, so for example, there are some cases where the mean can be fluctuated, okay, or deviated from the exact value. So it is defined by variance, okay. So the expected value of a square deviation from the mean of the random variable x, okay, is nothing but the variance. So generally, variance is denoted by the notation sigma square, okay. So here it is also called covariance. So for a random variable x with the probability density function fx of x and its mean as mu, the variance of x is denoted by sigma square equal to expectation of x minus mu whole square, that is equal to minus infinity to infinity x minus mu whole square fx of x dx. Did you understand? So when you subtract mean from the random variable and find the square value, and when you multiply that by probability density function and find its sum over the given interval, then you can find the variance of the random variable. Okay, here are some properties. Okay, here variance of x can also be defined by using this expression. Variance of x is nothing but E of x minus E of x. E of x in the sense mu, okay, x minus mu whole square. So it will be also equal to E of x square minus E of x whole square. That means what? So when you find the variance by using first formula or by using this formula, that means expectation of mean square value minus the mean square, okay, E of x whole square in the sense mean square. So if you find simply like this, those both will be the same. So variance of x is given as E of x minus E of x whole square. Okay. So when you expand this equation, so x square minus 2 into x into E of x plus E of x whole square. So expectation of x square minus, so expectation when you applicable this E of x, this expectation to this x, it will be expectation of x. Do you understand this equation? So when you distribute this expectation for the x, so it will be E of x. So that is why I have written 2 into E of x into E of x plus x square. So E of x square minus, so 2 into ex of E of x whole square plus E of x whole square. See, these two terms are same. So, but it is minus 2, but it is plus 1. So, if you subtract one value, you will get E of x square minus E of x whole square. Did you understand? So, here the first term is nothing but the mean square value, and the next one is mean square. Okay, so don't get confused. So first value is mean square value, next one is mean square. Okay, so this is the proof for the property. So expectation of x minus mu whole square will be same as expectation of x square minus expectation of x whole square. So next coming to standard deviation. Standard deviation tells us this is the actually spread or fluctuation or dispersion around the mean is nothing but the standard deviation. So mean is exactly central point. Okay. So how far the variation, okay, the deviation lies is given by the standard deviation. So standard deviation is simply the square root of expectation of x minus mu whole square. And here we have variance, okay, for discrete random variables. Okay, thus for a discrete random variable x with the px of xi, which are nothing but the probabilities of different events. Okay, discrete random variables where I equal to 1, 2, 3, and so on. So then the variance is given by the formula sigma square equal to sigma. The limits are from 1 to n because we have taken 1 to n events. So xi minus mu whole square, which are multiplied by their respective probabilities. And if you take the sum, then you will get the variance. Okay, so this can also be expressed as variance of x equal to sigma 1 to n pi into xi square minus mu square. Okay, so these are the properties which we have previously discussed on continuous random variables. The same will be applicable for discrete random variables also. Okay, so this first property sigma x square equal to E of x square minus mu x whole square. Okay, both are same. So if y equal to cx of plus b, so if it is a function, okay, so there where c and b are the constants, then sigma y square equal to c square sigma x whole square. So sigma y square is nothing but the expectation of cx plus b, okay, minus its mean square. Okay, so cx plus b minus, so here expectation of x is nothing but the mu x itself. So minus b whole square. Minus b gets cancelled. Okay, so we plus b minus b will get cancelled. So what we will be left with cx minus mu x. So take c common. So x minus mu x whole square. So e c square. I'm sorry. B minus b will get cancelled. Okay, cx minus mu x whole square. So when you expand this, you will get this equation: c square sigma x whole square. Okay, and if it is a constant, the variance would be 0. So next, central moments. So central moments, I have told you already, the mean is the first moment and the mean square value is the second moment. Central moments are nothing but the it is exactly what is the central value of how the probability, okay, how the variance is distributed along such certain interval. Okay, so the first central moment is 0 and the variance is the second central moment. And if you want to find the nth moment of the random variable x, which is nothing but e of x over n, integral minus infinity to infinity x over n fx of x dx. Okay, where n has different values from 1 to n. And nth order central moment is nothing but the e of x minus mu x whole power n, which is nothing but minus infinity to integral minus infinity to infinity x minus mu whole power n fx of x dx, and where n is 1 to n. Did you understand? So here moment is nothing but the expectation. Okay, central moment is nothing but related to variance. Next, coming to the characteristic function. So generally, characteristic function of a random variable defines the probability distribution. So probability distribution, how the probability is distributed over certain interval. Okay, so it's nothing but the probability distribution. So here characteristic function is also tells us the same. Okay, so that is why the characteristic function is nothing but the Fourier transform of the probability density function, which is defined by using the formula phi of omega equal to expectation of e power j omega x. So if you find the integration for this, it will be minus integral minus infinity to infinity. Okay, so pi of omega equal to e power j omega x equal to integral minus infinity to infinity e power j omega x fx of x dx. That is how we can find the characteristic function. And we can get the fx of x, which is nothing but the probability density function, by simply taking its inverse. Okay, fx of x equal to 1 by 2 pi integral minus infinity to infinity pi x of omega e power minus j omega x d omega. So only the changes you have to notice here is, for Fourier transform we get e power minus j, whereas for inverse Fourier transform we get e power j omega x. But here only the signs are varied. That's it. Okay, here is an example for finding of characteristic function of the example which we have discussed earlier. Okay, consider the random variable x with probability density function fx of x given by fx of x equal to 1 by b minus a, which is distributed over the interval a and b, 0 otherwise. Then the characteristic function generally can be found by using Fourier transform. Pi x of omega equal to, so the interval here we have a to b, 1 by b minus a e power jx. So here 1 by b minus a is constant, so take it outside of the integration. Okay, 1 by b minus a, and what is the integration of e power j omega x by a? Okay, so e power j omega x. So its integration is nothing but the e power j omega x by j omega. Okay, so over the interval a to b. Now apply the limits. So 1 by j omega b minus a. So e power, where we have to substitute the limits in place of x. So e power j omega b is upper limit minus e power j omega a, which is noted as the lower limit. And it is the characteristic function of a given density function by using Fourier transform. And similarly, for a discrete random variable, the characteristic function is nothing but the summation. Using, we can express that in terms of summation. Pi x of omega equal to expectation of e power j omega x, which is nothing but sigma xi, which is belongs to Rx. Rx is the set of integers. Generally, we limits from 1 to n. Px into xi e power j omega xi. So Px of xi are the probabilities of different discrete events. Okay, and e power j omega xi. In this case, pi x of omega can be interpreted as a discrete Fourier transform with e power j omega x substituting e power minus j omega. I have told you already, only the sign change is possible in the case of characteristic function. So in the original discrete Fourier transform, the inverse relation is Px of k, which is nothing but the probability mass function, which is obtained by using the expression 1 by 2 pi integral, okay, minus infinity to infinity. Our particular values we can take minus pi to pi e power minus j omega x, sorry, e power minus j k, okay, in terms of k, okay, because it is discrete Fourier transform. So pi x of omega d omega. So we are ending this session with the characteristic function. Thank you so much.